Hey guys, this is Mr. Lowry. This is an activity that we started in class on November 23rd, which is a Monday. So if you're in cohort A, excuse me, that's when we did this. If you're in cohort B, then this would be from 11/24, which is a Tuesday. So we started it in class. Your homework is just to finish up this activity. So I'm going to get you started in here. We're going to talk a little bit about what we call parent functions and function families, and I'm going to show you how to graph some functions that you may not know what they look like starting off, okay? So as you go through this, you should read everything in here. Read all the way through it. Make sure that you kind of understand what's happening here. I'm going to talk through it a little bit, but you should still read all the kind of paragraphs in between, all the instructions, and answer all the questions as you go. Again, this is just going to help you get started. I'm not going to go through everything with you in detail. You can do some of this on your own, but I do want to give you kind of a head start here. Okay, so what we're doing in this activity is we're talking about function families. There's all different kinds of functions, and we can classify them into different groups based on their characteristics. One of those groups or one of those families that you are probably familiar with is linear functions. Okay, so linear functions form a family because they're all kind of similar. They're all lines. They all have a constant rate of change. Okay, so we have this family, linear functions, and what we do is we pick the most basic version of that function, or the most basic version of that shape, and we choose that to be the parent function, which is almost like the mascot for the whole family. It's like the original. Okay, so here's a parent function. Okay, and this is almost, again, kind of like a mascot, something that represents every other function in the family. They're not all identical, but they're similar to this guy. Okay, you can also think about this as an original. I forgot to spell original. Okay, something like that. Okay, so what we want to do here is we want to take this, what we call parent function, and we want to graph it. We want to see what it looks like. So another way to write this is y equals x, right? F of x equals x, y equals x. They're kind of similar. And in order to graph this, what we need to find is the slope and the y-intercept of that function. Well, if you think about it for a second, slope-intercept form looks like y equals mx plus b. So this is the slope, this is the y-intercept, and the slope is usually that number that's in front of x multiplying it, and the y-intercept is usually a number after x that you're adding or subtracting. So when you look at this and you don't see those numbers, you got to assume then that this is y equals 1x, right? If there's no number in front of x that's multiplying it, it's got to be an invisible 1. If there's no number behind it that's, adding or subtracting, then that's got to be a plus 0. So our slope is 1 and our y-intercept is 0. If we want to graph this thing, then we start with the y-intercept, should be at 0 or 0, 0, this point here called the origin, and then the slope is 1. We can rewrite that slope as 1 over 1, right? So this is the rise over the run. It goes up 1, right 1, up 1, right 1. So to get to the next one, we go rise over run, 1 over 1, up 1 over 1, up 1 over 1. Okay, and we can start to see the pattern. Since we know this is linear, we can kind of connect the dots here, and we'll get a pretty good idea of what our parent function looks like. So I'm just lining this up, trying to be careful. Okay, that looks pretty good. Now this arrow obviously is going to keep going in either direction. Okay, so that's the parent function. It's like the most basic linear you can get. It has a very basic slope, a slope of 1, right? The most basic slope you could get. It has the most basic y-intercept you can get. So pretty boring linear function, but that's okay. It's like kind of the mascot for all the other linear functions. Okay, we want to just practice with our key features. So domain, range, increasing, decreasing. So the domain is, we go from the smallest x to the biggest x. But this arrow, it's going to keep going. This function is going to keep going down and to the left and up and to the right. So if you're trying to look for your farthest left point, like it keeps on going. So you can't find a smallest point. The smallest point that fits on the graph is -10, but that doesn't mean the line stops there. It means it's going to keep going. So our lowest value for x is negative infinity, and our highest is positive infinity, right? Because this arrow is going to keep getting bigger and bigger. We can't really find a lowest or a highest x. So we just say negative infinity to infinity. This line covers the whole x-axis. In this case, the same is true for range. The lowest y value, we don't have one because this keeps going down. And the highest y value, we also don't have one because this thing's going to keep going up forever and ever. Okay, so your domain and range are negative infinity to infinity, and another way to say that is to say all real numbers. The positives, the negatives, the fractions, all the in-betweens, all the way up to infinity and all the way down to negative infinity, all those are included in your domain and range. So ARN stands for all real numbers. It's another way to represent that. Okay, let's look at increasing for a second. Now remember, increasing is kind of like uphill and decreasing is downhill. So when are you going uphill, when are you going downhill? Well, if I have a little guy here and he's walking uphill, when he goes to the right, he's always hikes to the right, he's always going to be going uphill. There's never a time where he's not going uphill. So he's increasing over the entire domain. There's no part where he's not increasing. And he's never decreasing. If he's walking to the right, he's never going to be going downhill. So don't worry about that one. It doesn't really make sense. Okay, let's talk about positive negative. Positive negative is kind of like above the water, below the water. So we think of the x-axis as like maybe a body of water. And if we're below the x-axis, then we're negative, and if we're above the axis, then we're positive. So that changes right here. He switches from negative to positive right at this point. This line divides our graph into the negative section where he's below and the positive section where he's above right here. So the negative section, again, remember there's no farthest left. It's like negative infinity. The negative section goes from negative infinity all the way up to 0, and then it stops at 0. The positive section starts at 0, like right at this point. As soon as he passes 0, he comes out of the water, and then he's positive for a while. So it starts at 0, and then he's positive until infinity. So we kind of break up our domain into this section and this section in this case. Okay, last one for this page. We want to write any other linear function. Okay, it needs to be in slope-intercept form, and we're going to use function notation, but we can pick pretty much anything we want. Okay, now it needs to be in slope-intercept form, so we're looking for something that looks like this. So just go ahead and pick any slope. Let's say 3, and let's pick any y-intercept. Let's say -4. Okay, now when we talk about this linear function, we say that this is just a different version of the parent function, right? The parent function is this most basic, the mascot for all of them. So this is a linear function too. It's just a little bit different than the original one. And we want to maybe describe that difference. So let's take a look at what this graph would look like. Here's your y-intercept, -4, down here. And this is going to go up 1, 2, 3, and right 1. This is the slope. So intercept, -4, put it down here, it's the y-intercept. Slope is 3, or 3 over 1, which means we rise 3 and we run 1. We go up 3, right 1. So to find my next point from the y-intercept, I go up 3, right 1, up 1, 2, 3, right 1, up 1, 2, 3, right 1. Okay, so this isn't the parent function anymore. This is a different one. But how do they compare, my new line and my old line? Well, it's still a line. It still has a constant rate of change, but it's steeper and its y-intercept is lower. So how does the new linear function compare to the old one or the original one? So we would say that it's steeper and y-intercept is lower. Right, something like that. When we take the original function and we change it somehow, we call that a transformation. Any linear function that's not this original one, we think of as like a translation, or a transformation, of the original. So we could say, if we took this original function, this parent function, and we made it a little bit steeper, and we moved it a little bit farther down, we would get to this new line. So that's the relationship between a parent function and one of its transformations. Okay, now again, you got some reading to do. So read through this section. Okay, this will help you kind of understand what's going on and what we're going to do. Okay, in this page, on this page, we have a brand new family of functions. Okay, it's called absolute value functions. So it's a different family. They're not linear. These aren't going to come out as straight lines. I'll give you that hint right off the bat. This is the parent function. This is the mascot, or like the original or the most basic version of an absolute value function. Okay, we've dealt a little bit with absolute value before. What we want to know is it's the distance from 0. So if I had absolute value of -3, what that's asking me is how far away is -3 from 0? It's 1, 2, 3 spaces. So the absolute value of -3 is equal to 3 because it's 3 spaces away. Okay, the absolute value of 4 is asking you how far from 0 is 4. Okay, well, it's 1, 2, 3, 4 spaces away. So absolute value of 4 is 4. That's how we evaluate an absolute value expression. This is our function. So when we're trying to graph something and we have no idea what it looks like, what we can do is we can pick, just kind of maybe almost randomly pick some x values, some input values, and then see what their output values are. If we take some numbers and we plug it into this, we'll get some things that we can graph. Okay, so we're going to pick some input and output values. Okay, now we can pick, a variety of different ones. We want some negatives, we want some positives, we want to get a good idea of what this graph looks like. If we pick enough points, we'll be able to plot those points and see what this function is, what this function graph looks like. We have no idea what it's going to look like. So let's take a look. Yeah, I'm going to pick a few input values here. Let's say -3, let's say 2, let's say 1/2, 0, -4, let's do 5, and let's do, let's see, we got some negatives in there. Let's do -1. Okay, so this is where our x's go. This is our x. And this over here, the output, this is basically our y value. We say f of x with function notation, but that's essentially what it's going to be. These are going to make a coordinate that we're going to graph. The middle section is for you to do some work, because we're going to have to do some evaluating. So if we know the x, we can plug that into the function and evaluate to get the output. So even though we don't know how to graph this kind of function, it doesn't matter. We know how to evaluate, and so we can use inputs and outputs. So if this is my input, then I want to find f of -3. I want to find the output of the function when the input is -3. So I plug in a -3, right? I replace the x's with -3, and I evaluate this side. What's the absolute value of -3, or how far away is -3 from 0? It's 3 away. Okay, let's do the next one, f of 2. Okay, well, that's the absolute value of 2. How far away is 2 from 0? It's 2 away from 0. Okay, then we have f of 1/2. Kind of funky. It's okay, we can do fractions. How far is a half from 0? It's 1/2. Okay, so here's the pattern. The negative guys are becoming positive. The positive guys are staying positive. Okay, kind of similar to what we had up here. Okay, let's do f of 0. So that's the absolute value of 0. How far away from 0 is 0? It's 0 away. Okay, let's do f of -4. So that's the absolute value of -4. How far away is -4 from 0? It's 4 spaces away. f of 5 is equal to absolute value of 5. Again, absolute value of 5 is just 5. And then f of negative 1 is the absolute value of negative 1, which gives you a 1. So input, do a little bit of work. This is where you just kind of plug it into the function and kind of see what's going on. And then you evaluate and you get the output. These are all coordinates now, right? So negative 3, 3 is a coordinate. We need to plot that guy. Negative 3, 3. Okay, 2, 2 is a coordinate. So let's plot it. 2, 2. Okay, now if we knew this was linear, we could connect those two dots and be like, done. We got 2 points, connect them with a line, we're done. But we know this isn't in the linear family. This isn't like slope-intercept form. We have an absolute value. This is a different type of function. Kind of weird. Okay, so let's pick another. Let's do another point. Okay, we have 1/2, 1/2, right? So half, we have to estimate here. It's like halfway between 0 and 1, and then up halfway between 0 and 1. Okay, so something like that, kind of in the middle of that first square box. Okay, then we have 0, 0. That's right here. Okay, the origin, we call that 0, 0. We got the point negative 4, 4. So negative 4, 4. Okay, and then we have the point 5, 5. So 5, 5. Again, these are just coming from these numbers, right? Input, output, x, y. These are basically coordinates now. Negative 1, 1, that's a coordinate, x, y. So negative 1, 1 is going to be right here. Okay, so now we got several points on here. We're starting to see a pattern. We're going to look for that pattern, and then we're going to try to like do some inference here. Now we picked some specific values here, but we could have really picked any values. When somebody hands us a table or gives us like a list of coordinates and say, hey, this is a function, then we can't assume that there's any other points for that function. But this, we weren't given a table, we were given a function. We could really have picked anything we wanted for an input and gotten an output for it. So although it looks like we have a very short list of points, this is not a discrete graph. This is a continuous graph because we could have chosen any input value. We just only chose a few. So we're going to connect these guys and see if we can see this pattern. So it kind of looks like this. Now at this point what you're going to do is you're going to go to Desmos.com. This is part of your assignment. Okay, Desmos.com is an online graphing calculator. It's free. It's super easy to use. And you're gonna graph this function. You're gonna make sure it looks good. So on your keyboard, there's a little button that looks like this, and it has like this symbol, and it has this symbol. It's right under the backspace key and above the enter key. So in order to type absolute value, when you go to Desmos.com, you do F parentheses X, or you could also use Y to make it easier on yourself. You go equals, you do shift and then hit this key so you get a line, a vertical line, and then you write X, and then you do shift in this key again. And that's how you type it in your grapher. And then you graph it. So you can do this, or you can do Y equals absolute value of X, kind of like that. Either one will give you the graph, and you just want to check and make sure, does it actually look like this? Okay, so you want to double check. This is kind of a guess. We picked some points. We hope it looks right. We hope we picked enough points and we picked the right points in order to make this work out. But we want to check using a graphing calculator, graphing software. So use your Chromebook, go to Desmos.com, open up the graphing calculator, and use that to kind of help you graph this guy. All right, now let's go down here and let's kind of talk about what we're seeing here. So this is a V shape, and it turns out that any other function and that has an absolute value, any other absolute value function is going to be a V shape. Now it may not be exactly the same V shape. It could be steeper. It could be upside down. It could be moved to the left or to the right. but any absolute value function is going to be a v-shaped function. Okay, in this case, we want to find domain and range, increasing and decreasing again. So this arrow goes forever to the left, and this arrow goes forever to the right. So I can't pick a smallest x value. This is just going to keep getting smaller. This arrow is going to keep going over. There's no smallest x value I can pick, and there's no biggest x value I can pick. So that's my domain again, just like I had before. For the range, there is a smallest value, right? There's no way I can end up down here on because if I pick a negative number, I just end up getting a positive number. And if I pick a positive number, I end up getting a positive number. There's no way to get a negative number out of this absolute value function. So my smallest value is 0, and my biggest value is infinity, because these arrows keep going up. So from 0 to infinity is my range. I can't be down here in negative land. Okay? Again, the graph kind of splits in half. This side of the graph, we're increasing, and this side of the graph, we're decreasing, because remember, our little hiker guy is going to walk from left to right, and he's going to walk downhill for a while, and then he has to turn around and walk uphill. So our interval where we're increasing is from here, from 0 up to infinity. Now we're talking about x values, right? So he's marching to the right for infinity. The decreasing interval, he's going downhill, right, from negative infinity way over to the left all the way to 0. He's going to go downhill. So we're looking for what values, what part of the x-axis is covered by this section of the graph. What interval for the x-axis. Remember, these intervals, increasing, decreasing, we're only worried about the x's. We don't care how high or low he is. We're just talking about what part of the x-axis is he decreasing on and what part of the x-axis is he increasing over. Okay, so from 0 to infinity, he's increasing. Negative infinity to 0, he's decreasing. Okay. Now, the next thing that you're going to do here is you're going to graph two functions together. Okay? You're going to graph this guy, and you're going to graph this guy in Desmos. You're going to type it out. So use that key that I talked about for your absolute value. It's below backspace and above enter. You want to graph both of these functions together and compare this guy to this guy. How is it different? This one's the parent function. This is the most basic, generic, absolute value function. It's like the mascot for all the other absolute value functions. This is an absolute value function as well. It's just like a transformed or alternate version of this one. So compare it back to the original, the kind of the prototype. How does it compare to the mascot function or the parent function? Okay, so that's very similar to what you're going to keep doing in this assignment. Okay, so let me kind of get you started on the next ones. We won't go through all of it together. You'll go through a lot of it together, or excuse me, a lot of it on your own. But let me help you get set up here. Okay, first off, don't forget to read everything. There's some important ideas here that I want to make sure that you understand. We've kind of talked through some of them, but you should definitely read those and make sure you understand those ideas. Okay. Now, this is an entirely new family of functions. We have no idea what it's going to look like. It's not going to be V-shaped. It's not going to be a line. It's going to be a different kind of shape. So just kind of plan for that. This is the parent function for this family of functions that's called quadratic. F of x equals x squared. Okay? I'm going to try to make your life a little bit easier here by giving you the inputs. Now, you can pick whatever inputs you want, but sometimes they don't fit on the graph if you choose ones that are too big or too small. And usually I choose, some negatives, I choose some positives, I try to get a good idea on both sides of the axis. So these inputs that we're picking are not the only possible inputs. I'm just choosing random stuff. We're going to basically grab a sample of inputs, we're going to throw it into the function, see what we get, and hopefully we get enough points to get an idea of what the graph looks like. So whenever we're graphing a function and we have no idea what it looks like, we're going to plug in points until we find enough points to see a pattern. So here's the inputs I would use. Okay, don't necessarily use those every single time, but those are good ones for this function. Okay. Let me help you evaluate the first one because this is a lot of people make mistakes here. So the function f of x equals x squared says whatever the input is, square it. The problem that people have is they forget that order of operations is really important here. So I'm going to do f of negative 3, and when I plug in a negative number into a function, I always want to plug it into parentheses. So in this case, what I want to do is I want to have negative 3 in parentheses with a little 2 on top. So this is taking negative 3 and squaring it. Okay, the reason why it's important to use parentheses is because there's a difference between these two things. We've talked about this before, but ninth graders constantly forget this. Okay, this is what you want. This is saying take negative 3 and multiply it by another negative 3. That will give you a positive 9. Okay, this is not what you want. What this is saying is take 3 and square it and then make it negative at the end. This is equal to negative 9. Okay, this is how you square negative 3. This is not squaring negative 3. This is squaring 3 and then subtracting it. Order of operations says exponent comes before the subtraction. Okay, now in this one, if you square it and you have that negative inside, then you copy the negative as well, and when you have negative times negative, you get a positive number, and that's what you want here. Okay, so whenever you have these negative numbers, when you're trying to square them, put them in parentheses, and you should only get positive numbers out of here, because a negative times a negative is a positive, and a positive times a positive is also a positive. Okay, so graph this guy up. Again, you're going to go to Desmos. You're going to double check your function, make sure it looks good, make sure it's the same thing. If you made a mistake, go back and fix it. See if you can find out where you made that mistake in your table. Find your intervals here. On what interval is it increasing? On what interval is it decreasing? On what interval is it positive? Find your domain and your range and see if you can figure out a description for the shape. Okay, all that you'll do on your own. Okay, also in Desmos, you will graph these two functions. This is the original. It's the most basic version of a quadratic function. It's the parent function. It's like the mascot for all the other quadratic functions. It's the most basic version of it. This one is a different version of it. It's a little bit got a negative out on the front, so type it exactly like this here. And see what they look like. Okay. Now, if you want to type an exponent in Desmos, here's how you do it. You can, if you want to, you can use y for these instead. But you could go like f of x equals, okay, then you go x, and then you go shift 6. So on the 6 key above the keyboard, there's a 6, and then there's this little symbol above it. Okay, that's called the caret. Okay, so if you go shift 6, it's going to do this guy, and then you write 2, and it'll make it look like an x squared for you. You'll be able to see it there. Okay, so shift 6 gives you the symbol that you need to basically raise this to a power. Okay, then you'll type again, like for the other one, g of x equals negative x caret 2, and that'll make it look like this. Okay, see what they look like, compare them. Okay, you got a couple more. I'm going to help you pick the inputs and outputs because I think this will make your life easier. Okay, again, read. Okay, read through this this text here. Try to understand what it's telling you to do. Read the directions. Okay, make sure you're following directions here. Okay, this is a completely different family now. This is the square root function family. So it's not going to be the shape of any of the other ones that we've seen. It's going to be a completely different shape. So let me give you some inputs that'll work really well. Again, these aren't the only ones that you can choose. You can actually choose whatever input you want, but these will be good ones to use. So I would choose 0, 1, 4, 9, and that's probably enough, honestly, to get you where you need to go. So let's kind of do that one. So this is a square root function, okay? The square root function is basically asking what squared gives you that number. For example, the square root of 25 is saying what squared gives you 25. The answer is 5, right? Square root of 16, what squared is 16? 4. 4 squared is 16, so the answer is just 4. Okay, square root of 49, what squared is equal to 49? Okay, it's 7. We got to pick numbers that are going to land on the graph, though. These are all 25, 16, 49. Those are all too big to fit on the graph. And so we have to pick things that are smaller. So these will work really well. Let me do one with you. F of 9 is equal to the square root of 9. Okay, so we're just plugging it in, evaluating. What squared is equal to 9? Well, the answer is 3. 3 squared is equal to 9. So the square root of 9 is equal to 3. So here's your coordinate, 9, 3. So 9, 3, okay, that's one of your points. So find the other points and see what it looks like. Okay, another thing to think about is you can't take the square root of a negative number, which is why I didn't choose any negatives. Okay, there's some operations that you can't do with negatives, and square root is one of them. Let me see if I can explain why. If you take negative 3 and you square it, you get a positive 9. If you take positive 3 and you square it, you get a positive 9 as well. So if you're going to try to take the square root of negative 9, what that's saying is what number squared gives you a negative 9? And there's no way to get there. There's no number that when you square it will give you a negative number. If you square a negative number, you get a positive. If you square a positive number, you get a positive. So there's no number that you can square that'll give you a negative 9. So this just doesn't work. You can try typing it in your calculator and it'll say like error or something like that. You can take the square root of other numbers, like you could take the square root of 2, but it doesn't come out nice. It comes out as a decimal. You can take the square root of 0.5. Again, it's going to be a decimal. So use these inputs. See if you can get a good look at your what your graph looks like. And then you're going to go to Desmos, graph it on Desmos, see what it looks like, see if you got it right. Okay. Now, if you're in Desmos, here's how you type square root. If you type SQRT, those letters, it will turn this into this symbol for you. It'll go boop, and it'll change over to this. So you want to write like f of x equals SQRT, and then it'll change to that symbol, but it'll go boop, and then you can type in an x inside of it. And that's how you're going to graph that guy. Again, you want to find your intervals, increasing, decreasing, positive, your domain and range, things like that. And then you're going to graph another one, comparing the original, the parent function, the most basic version of a square root function, the mascot for all the other square root functions. Compare that to this guy, which is a little different because it has a 5 in front of it, 5 plus. How do they compare? What's different about it? Okay, last one. Again, I'm going to give you your inputs. Sorry, kind of spaced for a second. Again, you can choose a lot of different things. You can choose a lot of different numbers and make this work. The trick is, how do you get it to land on the graph? Because sometimes if you choose the wrong number, it'll be off the charts or something like that. So let me give you some numbers that you can pick that'll work out really well. In this case, -3, -2, -1, 0, 1, 2, and 3. Okay, similar ones to what I've used before. They're not the only ones you can ever use. You can actually pick whatever input you want for this function. You can square whatever. The trick is making sure you have a good variety so you can see what the positive numbers give you, what the negative numbers give you. You want 0 in the middle for sure. You just want to get a good variety of numbers so you can see what this graph is going to look like. Okay, let's do the first input. Okay, f of -3 is equal to -3 to the third. Okay, -3 to the third is -3 times -3 times -3. This third means 3 copies. Now remember, like I told you before, you need to substitute the negative, or sorry, put the negative and the 3 in parentheses and then raise it to the third power. So there's 3 copies of -3 all multiplied. This part right here, -3 times -3, That's just equal to positive 9. So you take that positive 9 and you multiply it by another negative 3, and you're going to get negative 27. Okay, so because there's 3 negatives and not 2, negative times negative will be a positive, but then that positive times another negative will be another negative number. So fill this out, okay, and graph it. Okay, go to Desmos again, type it in, see what it looks like, double check, make sure you have it right, find your intervals where you're positive and negative, and then you're going to graph these two guys. Okay, this guy, the original one, f of x equals x to the third, is the basic cubic function. Okay, it's not going to look like any of the other ones. It's not a line, it's not a V shape, it's not going to look like any of the other families that we talked about. It's going to be its own thing. You got to kind of figure out what that looks like. This one will look similar to this one, but it'll be a little bit different. Notice this one has a -2 inside parentheses. So when you type it into Desmos, type it in just like this. Again, if you want to do a power, you use this key. It's above the 6, so Shift 6 will give you that guy, and then you can put a 3 there. Okay, so g of x equals, you type that right in on Desmos. Take a look at your graph, and you'll be able to see what it looks like. Okay, so that gets you started. That's almost all the way through. Now, we did this in class, and of course, in class is about 50 minutes or so. So I've almost got you there. You just need to kind of finish it up, finish those evaluations, finish those graphs, and yeah, we'll talk about it a little bit more next week when you guys get back. Have a good Thanksgiving.